Thank you. I'm going to take things in a slightly abstract direction, and we're going to think a bit about some of the things I've discovered and noticed along the way, doing this sort of knowledge sharing work, and I hope give some idea about some new things that are coming and maybe some things that you can take advantage of as we go forward. And we're going to start our journey today with a train. Not just any train. This is actually a driverless train in the Singapore transit network. Not that I've ever actually ridden on this or even seen it or been to Singapore, but it actually has something to do with this because at the time I was working on my part of this. This is an X-ray observatory being built by the European Space Agency, and in my little corner of this, I was hidden away in the lab working on some real-time software, solving some problems which turned out to be the same problems that the people working on this transit system were solving. Now, I wasn't going out looking for this. What happened was, through one of those sort of serendipitous contacts, they found me, and it turned out that the particular technique I'd sorted out in my application was the very thing they needed to sort out their signalling. Signalling turns out to be more exciting than you think it does. It's a tough sell. But what you're seeing here, what you're really seeing is that over here, spacecraft are a bit on the expensive side. Take it from me, it costs a lot of money to launch them also, so we tend to be very careful of them. And one organisation's mission critical turns out to be another organisation's safety critical. And it turned out that we actually had quite a lot of overlap in some of the things that we did. So that was a sort of an initial example where I got plucked. If I say from obscurity, that implies that I'm not still obscure, but I'm working on that meeting by meeting. A slightly more abstract example, this is a telescope. This is a Retina. People who make telescopes get very bothered by the atmosphere. Okay, it turns out to be very inconvenient. Even if you put your telescope at the top of a mountain, the atmosphere still does pretty filthy things to the quality of the light you get in. Now, a lot of very useful and expensive work got done in the area of adaptive optics. So now we've got techniques that are used routinely on telescopes, which, if you like, untwinkle the starlight and make it possible for astronomers to do much better astronomy, even without using spacecraft. Though, obviously, I still think spacecraft are interesting and a useful idea. But why the Retina? Well, there's two reasons why I pluck this example out. One, it turns out that if you're an ophthalmologist wanting to look at a retina, and you're looking through the lens at the front of an eye and then through the liquid inside the eye, you're seeing some of the same sorts of problems that an astronomer has looking through the atmosphere. The liquid in your eye is soupy and it messes about with the light coming through it. So there's a limit to how accurately you can look at the retina. And people are already now publishing papers using adaptive optics techniques created for astronomy, but used looking through the lens of the eye, and are now able to image down to the degree of an individual rod or cone cell. So this is pretty revolutionary, if you're interested in that sort of thing. The other reason why I picked this example is because it has an example of what I'd like to think of as the along the way effect, which is that one of the devices you need to invent if you're going to do adaptive optics is you need to be able to measure what the distortion to the light is. Okay, and the device that we create for that is something called a Wavefront Sensor. I'm not going to explain how that works now. I've got to leave something to talk about over coffee later. But a Wavefront Sensor turns out to be quite a useful device in other applications, not connected with adaptive optics. The term you're most likely to have come across, I suspect, is some of you may even have had laser eye surgery. And sort of the most, I suppose, the gold standard of that at the moment is actually billed as wavefront corrected laser eye surgery. And this works by actually using this wavefront detector as a method for measuring the shape of the eye in a way that's more accurate than you can otherwise. So this is a product which is, if you like, a byproduct of the need to solve the problem for the astronomer, but has a lot of uses elsewhere. Final example in this set, this of course is a bridge. And these are some optical fibres. We're used to the idea of fibre optics being useful because what you want to do is send light down the fibre and keep it in there. But you can also do interesting things if you play with that fibre and put scratches in it. And one of the things that people are doing now is that if you put a collection of scratches in the edge of the optical fibre, the light will leak out of them. But if you send a pulse of light up and down, you'll get reflections coming back. I can see you're thrilled already. You wait till I get to the punchline. Why that's exciting is that it means that if you look very carefully at these pulses as they come back, you can detect what's happening to the fibre as it gets bent. And it's a fantastic way of making a strain gauge. The reason that's interesting is that you can make these strain gauges really, really cheaply and embed them into things like bridges. There's a lot of new work going on making bridges out of plastic at the moment. But people who make bridges and buildings tend to be very interested in long-term measurement of things like strain. And this has sort of dropped out of work on fibre optics. Now, the interesting feature about these sorts of odd examples, you'll have detected that I can talk for hours just on this particular topic. But the interesting feature here is that you need to know things that other people have got. You need to know about their problems, and people who've got problems need to know about what you've got. So that's getting a bit wordy. What's the shortest way of saying that? Well, I suppose lesson one, there's no substitute for talking to end users. This is the first thing I've found in a big way, which is that if you're working on the lab side, it doesn't matter how good your imagination is, you won't know really what the end user needs. And it might be from a marketing sense or which bit of their product they need the help with. It really helps. Talk to the end user. And likewise, the other way, if you are a user potentially of some technology or you're looking for some technology, don't assume that people in the university or in the other company, whoever you're working with, you can't assume that they understand what your problem is, because sometimes your experience is unique. So I work, as you've detected, in this knowledge transfer network now. I'm no longer part of UCL. And the history of this, where we get to today, not going to test you on this, not going to explain all of the abbreviations. What I wanted to illustrate in a simple way was that we've got quite a rich history of different types of organisations that have been set up and had a certain life in different sectors, under different sponsorship. And I suspect if I investigated further, I could push this further into to the left and find further things into the past. But from our little view of the world, it's culminated over here with the ESP KTN. David will pick up more about the philosophical differences, but the interesting break point is this one here, which is the point about 3 years ago when the Technology Strategy Board became an arm's length body and inherited a number of products, including us KTNs, and then had to decide what to do with them. And amongst the philosophical differences that happened were the styles of these networks were different. They were doing different things, maybe in different sectors, working in different ways. But what we need to do going forward is different. There's just a few key operating principles that turn out to be really useful in these networks that we do. And one of them is this business about trying to make sure that people who don't normally meet do so. so that we can get this knowledge sharing, but not just technical people in a domain meeting other technical people in the same domain. That's useful, and we'll always do some of that. But where the gold dust comes out is when you get people working across domains. And our way of doing that going forward is to think very much about challenges. So in ESP, what we're doing is we're thinking about challenges. So we have a few headline challenges. Quality of life technologies is one. So I say to ourselves, we've got all sorts of new capabilities here. What can we do? What are the problems? And in having this as a challenge for us, what it's forcing us as a KTN to do is to get out there and build our network by not only accruing new people who we already know, or obviously we don't know them yet, but not just accruing people making technology, but bringing people into the network who have problems in these sorts of areas, how to help elderly people live at home for longer, different medical problems, not just medical things though, there are things like access to better quality food, clean water, a number of things. Part of the rationalisation that has happened in the KTN optimisation is that we've got fewer KTNs, and that's made it much easier for the KTNs themselves to network together. So within this domain, quality of life technologies, for example, we already have a group of people interested in environmental monitoring. They make technology for doing it. And in the environmental sustainability KTN, they have a group of people interested in environmental monitoring because they own a problem. So that's great for us because it's easy for us to bring those two together and make sure that the people with the technology are meeting the people who own the problem. So for us, there's quality of life technologies, secure world. There's the sort of defence and security angle as well, but really we're, I think, perhaps more interested at the moment in things like civil resilience and, if you like, security from that sense rather than the defence market as such. Smart moves. We love to move things around. How can we make better vehicles? How can we make vehicles work better? How can we make better use of the infrastructure that we've got? How can we reduce the need for travel? These are big questions. We've already started a new program of activity working with somebody at DEC, that's the Department for Energy and Climate Change, as a result from us just changing our mindset to stop thinking about how we can push our technology out to making the step of going out and saying to people, look, we know you own this problem. What can you tell us about it? What are the really important things that we could help make an impact on?